Hi, everyone. Thank you for coming. Thank you for joining on Zoom as well. My thesis defense, I guess. Awesome. So title of my work is fairly long, evaluating real-world obstructed radiation view factors using hardware-accelerated single and double area integration algorithms. We'll get into what all of that means. Of course, my committee, Dr. Berry, Dr. Ricka, Dr. Hodnecki, and Dr. George are all, they're all here, which is wonderful. So we have a couple of things to cover, of course. We'll get into this, starting, of course, with the introduction, but just to begin with, if you've read the thesis, some things are, in fact, out of order for the sake of the presentation. Some things are in here that aren't in the thesis, which is wonderful. Source code, if you're interested, is at this repository. You can go read all of it. You can try to build it if you'd like. Verification tests, those are also all here. You're welcome to run those yourself on your own computer. And the hot shoes study is also here. That's the application for this work. And lastly, the organization is also on GitHub. You're welcome to go look at everything else that's on there. There are a couple of more things. So, introduction, why does this work exist? So NASA JPL, Jet Propulsion Laboratory, uses RTGs, radioisotope thermoelectric generators, for things where the sun won't really do the trick. So for example, deep space probes like the Voyager missions, or Mars rovers like the Perseverance rover, they have RTGs on board to provide power to all the sensors and motors and everything else on the piece of equipment. And so just to give you a sense of what that looks like, we have two images of the Perseverance rover. This one is from the lander itself as the landing sequence is happening. That's from the rover. And the RTG is this boxed thing at the back. So that's generally where that's located and what it looks like. They're good. They're reliable. They last a long time. That's why JPL uses them for all sorts of different missions. However, we need to better understand how they actually function. And so the purpose of this work is to serve as like a piece, a puzzle piece in the broader work of the group to better model how RTGs work so that before they send things up in the future, they can understand exactly what the performance characteristics will look like throughout the lifetime of the device as it's going. So this is a scale model of what it looks like. It's actually more stacks, and we'll see that in a minute. But inside, we have these bricks colored in blue. Those have plutonium pellets inside. And so as plutonium decays, that releases lots of energy. And so these bricks get fairly hot over time. And then those radiate out to these hot shoes, these little plates on the outside. And those hot shoes behind them are thermoelectric legs. Thermoelectric converters in general will convert a thermal gradient into a potential gradient and produce electrical power. So these are all connected in various electrical ways to power the overall device. And this work is applied to evaluate the view factors from the bricks to all of those hot shoes. That is the purpose of this work. So what is a view factor? Well, in general, it is a measure of how much one object can see another object, or in other words, how much of its field of view is taken up by another thing. In the context of radiation, that is important because if an object is radiating in all directions, how much of that is actually incident on the other surface. It's a geometric quantity from 0 to 1. This boundary is relevant in like 2 slides, I promise. That's really just a statement that an object can't take up negative percentage of the field of view. Can you guys open the door? Can't take up a negative percentage of the field of view, and also can't take up more than 100%. Neither of those neither of the situations makes any sense. So that's our value Fij. This is a visualization just to give you a sense of what we're looking at. So picture 2 circles that are separated by some distance. The center of the circle intuitively can see the other circle more than the boundary of that circle. Or conversely, the boundary is exposed more to everything else than the center. So that's our view factor. How do we evaluate this? Well, we have an analytic equation here. It's 2 surface integrals, not that complicated. For the sake of computational efficiency, the trig gets converted into some vector math, and that's all fine and well and good. But these integrals can't be computed easily on a computer, so we do numeric integration. What does that look like? The first one is called double area integration. This is essentially just discretizing the equation we just saw and turning it into 2 summations. So this is essentially the same equation, except 2 sums instead of 2 integrals, and everything is awesome. The second is single area integration. The first step here is to convert the area integral on the second surface into a contour integral around its edges. And we end up with this equation here. I'm not going to go through the whole derivation, obviously, but that gets discretized into this form, which is what gets used in the actual solver. And so those two methods, double area and single area integration, are what get applied in the open view factor solver in all of this work. Why do we need meshes? So here we have two surfaces that are overlaid on top of the actual answer for parallel plates. There's a little diagram in the corner over there. And these surfaces here are evaluated from just the one geometry. There's one node in the middle of that geometry. And as we can see, they are both incorrect relative to the analytic surface underneath it. Single area is a little closer, but double area is particularly bad. If you see the axis, it goes up to 8. That is a violation of our boundary of 1. So this is very clearly incorrect. And we see the same thing for perpendicular plates. These are just two examples. Double area is egregiously not the right shape. And so the purpose of mesh refinement here is to put a bunch more elements on the surface so that we can more closely represent the integrals that we saw at the very beginning. The finite areas will approach the size of those differentially small areas by refining the mesh. Of course, it is important to control the quality of those elements. Really skew elements, so long and thin triangles are bad. Equilateral triangles are wonderful. And so we have 3 ways of measuring that in this work. The first one is aspect ratio, where we draw these 2 boxes for each vertex in the triangle. The aspect ratio of the whole thing is the biggest one of these divided by the square root of 3. That's documented by ANSYS. The second one, also by ANSYS, element quality, we follow this equation. This constant comes from ANSYS. It's great. And lastly, skewness. We take our triangle, create a circle around it, and then take the equilateral triangle that is inscribed within that and compare their areas to get our skewness value. So those are our 3 metrics for element quality. Those will show up a little bit later, but in general, for numeric integration, for all sorts of contexts, the ideal element is what we're striving for. And so the mesh generation algorithms will strive for equilateral elements according to these metrics. For real applications, we have to consider the shadow effect. This is the idea that not every pair of elements on the 2 surfaces can actually see each other. There are 2 ways that can happen. The first one is they can be just facing away from each other. And in that case, they're not looking, right? That's handled with what we call backface culling. The second method, or the second circumstance is they're blocked by something in the way. And that is handled with Muller-Trambor triangle intersection. So just for visualization, backface culling, these 2 normal vectors define the direction of the 2 elements. Are they looking at each other or are they not? Determines whether or not that value will actually mean anything. And the second case is intersection. So here we have the 2 triangles. They're not being intersected by that third one, whereas now they are. And so these would be culled away from the solution. So here's some math. The derivation is in the paper. It's much more complex than this, of course. But we have 3 criteria, 3 parameters to determine whether or not something is intersected. The first one is T, that's our intersection distance. Is the intersection between the 2 triangles that we're interested in? Yes or no? That's the last criteria on the bottom. U and V are coordinates inside of the triangle that is potentially a blocker, and those should be between 0 and 1, and their sum should be less than 1 as well, to make sure that we're actually within that triangle. And so, oh my God, I lost a slide. That's okay. Moving on. The boundary volume hierarchy. This is an implementation to accelerate Muller-Trambor intersection. So that algorithm we just looked at, if we want to intersect a ray with this woolly mammoth, for example, and determine whether or not it's blocked by this structure, we have to check every single triangle on this surface, and that can take a lot of time, particularly for large meshes. This is 100,000 triangles. That can take a while if you have a lot of triangle pairs to check that for. So what we do is use a BVH to segment all of the triangles into little boxes. If we zoom in on the tusks here, we're partitioning basically all of the triangles in the mesh into little regions shown here. And the idea is that to check whether or not something is blocked, we can check just a couple of boxes and then only the triangles in that last box, rather than checking every single triangle in the mesh. This is intended to make things faster. The trade-off is, rather than doing a whole bunch of inexpensive triangle checks, we replace that with a couple of expensive checks of nodes and then a couple of triangle checks. so that in theory, the whole thing should be faster and more efficient in general. This gets implemented in OpenViewFactor. As we'll see in a little bit, the implementation is not the best, and I'll talk a little bit about why. But the purpose of this is to make everything faster. This is a well-documented implementation in computer graphics, so we know that this does work. Last piece is this problem is considered embarrassingly parallel, which means that all the subdomains of this problem are independent of each other. In this context, solving for the view factor between any two triangles has nothing to do with solving the view factor between any other two triangles. What that allows us to do, first of all, it's massively parallelizable, and we can distribute the whole thing across a compute platform. This work is currently parallelized across the CPU. In future work, we would GPU parallelize this as well, because it is, somewhat trivial to do so. There's not much intercommunication between domains. How does all of this happen? First of all, the verification tests themselves, we have a bunch of them. Parallel plates, perpendicular plates that share an edge, circular plates, cylinders, spheres, and obstructions, where I'll test both the naive implementation of checking every triangle and using the boundary volume hierarchy. And so if we take a look at making these meshes, for some of them I use this thing called the disk mesh 2D algorithm. This treats the entire mesh like a truss. And so each of the nodes has a member between them. There's a repulsive force, and the idea is that the algorithm will iteratively update the positions of these until the whole thing is in equilibrium with itself. That's the idea of disk mesh 2D. The user gives it a signed distance function to represent your geometry. That can be a square, that can be a circle, that can be any other shape that you would like, and then a length to define how big the mesh should actually be. So an example, this is a distance function for a rectangle with some other nested functions. There's an example mesh. As we can see, it's not perfect. There are some pretty skew elements on the boundary there. That can be tuned a little bit with parameters inside of the solver, but there's a good example of one. And so we have a couple of cases, parallel plates, where analytic answer is here. These were all solved, I cited in a couple slides ago, but these are all solved not by myself. Perpendicular plates that share an edge, this is a particularly nasty solution. And then those that don't share an edge, this uses the previous solution as well to get the answers for these. The last one, the use of this mesh is circles. There's an example mesh as well. Now, I in this work used just a uniform mesh across the surface. There are ways to change the distribution of the elements so that if you wanted to, you could make it more fine in the center or more fine around the boundary. And that is all possible with disk mesh. I did not personally do that. So the result for circles, here we go. For cylinders, I use a custom algorithm, separating it into a whole bunch of panels that the number of triangles in the panel is defined here. And then wrapping that around a circle. So for a really fine mesh, we get this really wonderful geometry. The purpose of this algorithm is that the meshes, or the triangle elements themselves, are all uniform with each other. There's no difference in element quality. With this mesh, the problem is that we get 4 elements at the top and bottom, and that becomes relevant for the obstructing case that I use later. So I went with fully uniform elements, even though they're not perfectly equilateral. Analytic case here, solution, this is what it will look like for the verification tests. And then the last one is a sphere. So this uses the icosphere algorithm. It's based on the icosahedron, where each of those planes in the center has an aspect ratio of the golden ratio. It's wonderful. So the idea is that each of these little triangles gets refined using SLURP. If you're interested, I can talk about that later. Spherical linear interpolation is a wonderful algorithm that will refine these elements onto the surface of a sphere. And then we get a pretty consistently high quality mesh at the end. This is as opposed to doing other methods like the UV sphere, which is not included in my presentation, but that's another alternative that is bad for its elements. So if we track this one triangle, as it gets refined, we see it starting to resemble a sphere. And if we go really far, then we get a nice perfectly, or almost perfectly round mesh at the end. And so the analytic case here is actually fairly trivial. From the inside to the outside is just 1, because it can't see anything else, because it's inside of the sphere. Now our obstructions are the case that I'm presenting here is from the sphere to the cylinder in the middle. And so the answer here is based on previous configurations. This part here is the complement from the inner to the outer cylinder, and the area reciprocity relation gives us the other way. So that's the analytic case for obstructions. For the RTG geometries themselves, we're looking at, so if you remember the geometry from before, we have a GPHS brick, that's our heat source, surrounded by a whole bunch of hot shoes. Now, I'm only considering 4 columns of hot shoes. That is because this section of hot shoes is symmetric around the RTG, and so we only need these 4 to fully represent the entire axis. And then beyond that, I'm also only considering half of the stack down because it is mirrored the other way. So these 72 hot shoes give us a full picture of the view factors to every hot shoe in the RTG, and that allows us to create more precise models of how these things actually perform with work that is beyond mine. So for general dimensions, this is what the block will look like. For the hot shoes, they're separated by some distance, and they're on an octagon that is circumscribed by the radius of 3.01. So results. This is the fun part. Convergence. For all of our verification tests, parallel plates, non-sharing perpendicular plates, coaxial cylinders, and for spheres, they all converge very nicely. One thing to note, single area integration is more precise than double area integration. This ties back into the inherent advantages of single area integration over double area that we looked at in the very beginning. This will be a general trend. It is more precise and also more stable for various things. For perpendicular plates with a shared edge, this is a particularly heinous case for numeric integration. That shared edge, the elements at that shared edge tend to be very close together and can sometimes be poor quality, which is what's happening in this last data point here. And so if we take a look at the actual quality, I'm sorry for the numbers, all of the worst versions of each metrics are worse in the bigger mesh than they are in the smaller mesh. And what that creates is poor numeric results. So that is the reason for that slight divergence at the end, but in general, the convergence does still remain. For parallel disks, it is a very similar story in this data point here. But what I want to point out actually is that double area integration is actually more precise in this case. And that is because the boundary of the circle is being represented by straight edges, and single area integration is reliant on the fidelity of that boundary. And so with the straight edges, it's not going to be the most precise representation, whereas double area integration is just filling the area with a bunch of dots. It doesn't care what the boundary looks like. And so that is going to be more precise. With that said, it's also more sensitive to poor element quality. And that's what's happening where this middle mesh is the third one. This middle mesh is by far the worst one. And so that's the cause for that jump in error. Now for obstructions, they both get the same errors for BVH and also for the MTI. Now I ran one more simulation here because this was significantly faster, as I'll get to in a minute. But the jump in error there is actually not due to mesh quality. It is due to it just converging to the wrong answer. And that is a result of just poor representation of the surfaces. The cylinder is not a perfect cylinder. The sphere is not a perfect cylinder. And so the result is just slightly off. As we see, it's not diverging again. It is just simply converging past the true answer. So that's all the verification tests. For runtime on all of them, they basically show exactly the same trend, where they start off kind of nonlinear in the n squared space, or log space, with n squared as the number of element pairs. And then they trend towards linear with roughly a slope of 1. And that is the case for basically all of them, including all of the obstructions. Now, here's where the implementation of BVH is not ideal. There is a considerable difference in time between the naive implementation of blocking and the BVH implementation. And this is unfortunate, we'll say. MTI, the naive implementation, is very simple. The algorithm does not have very much code. There's not a lot of memory copies. BVH is a very complex algorithm with lots of copies of memory all over the place. We're reordering things. We're extracting submeshes and all this stuff. And so that code is just more complicated. I am not a perfect programmer. And so the current implementation is clearly slower. This can be addressed with optimization, both from static analysis of the code itself and also runtime profiling, figuring out where it's inefficient during runtime. That can very quickly be dropped. I'm confident that these results can be flipped fairly easily to mirror actual computer graphics results. For singular integration, we have this wonderful advantage where we can refine only one mesh and still converge. And so if we're looking at parallel plates here, singular integration is doing great, while double area is converging to altogether the wrong answer. And this is with only refining the emitting mesh, so the first of the two surfaces. Why is this possible? Well, due to the contour integral around the second surface, the singular integration algorithm is only reliant on capturing that boundary. And for squares or rectangles in this case, the boundary is fully defined by the straight edges of a triangle. You don't lose any fidelity there by having a lower refined mesh, and conversely, you don't gain anything by having more elements in the mesh either. And so if we just ignore the second surface, leave it as is, and refine the one, we see considerable runtime advantages, or runtime advantages by computing fewer element pairs. Double integration is reliant on integrating both surfaces, and so because we're not integrating both surfaces, it's just the wrong answer. This is true for both configurations of the perpendicular plates. This looks like it's diverging. It's actually just converging past the answer to the wrong answer. It's not getting better and then worse in the same sense, but same trend as well. This instability is again caused by the poor element quality right at the boundary between the two shapes. For the RTGs, this is the truly fun part. If we take a look at the view factors from each brick, so right now we're looking at the first brick to all of the hot shoes in the stack. Somewhat intuitively, the top, it's okay. The top hot shoes will obviously be viewed the most by that top brick, and this peak moves across the hot shoes very nicely as we go down the stack. As we get to this ninth brick, we're now in the center of the stack. The pattern has basically just reversed itself, and that is symmetry. It's beautiful. As we go down to the 10th and beyond, these results start to drop, of course. Now, I want to point out that while these results are all very similar to each other, the first column, meaning this red column, is viewed higher than by the bricks than these other ones. And this third column, which is this purple one, is not. That is the worst. And so the application of this in real life is the difference in view factors causes a difference in radiation, and a difference in radiation causes a difference in temperatures on the surface of the hot shoes. That difference in temperatures means less or more power through the thermoelectric couples at the back. And this has implications then on the performance of the overall device. So if the view factors of the hot shoes are all different, then the performance of each of them is also different. And so that has been explored. Carter did a study looking into that, and that was using all of these results as well. Now, if we want to assume that the whole stack is uniform temperature, which is probably not the case, but if we wanted to assume that and look at the view factors from the entire stack of bricks to all of the hot shoes, you see a very clear difference in the radiative potential, basically, where these two diagonal columns are significantly lower than the other two, which means that the two planar columns of hot shoes are going to receive more radiation, more energy from the bricks, and therefore produce more electrical power as well. Now, what can we take away from this? First of all, open view factor is verified against some analytic cases. These can be expanded if we want to do more. That repository has plenty of room to add more cases into it. Singular integration is generally more precise. Of course, that is reliant on the boundary of the second surface being accurately resolved. And as we saw with goals, that's not always the case. This also brings with it the advantage that if it is accurately resolved, then singular integration will converge faster and without refining the second surface, which is wonderful. Runtime is generally linear with n squared, where n is the number of elements on one surface. I did my best to keep the number of elements on both surfaces approximately the same, regardless of the configuration. So that was n squared was the x-axis on all the plots. BVH is not implemented as well as it could be, but can be optimized. And then RTG hot shoes have wildly different view factors from the stack of bricks, and that leads to different performances as well. Now, if we look at the whole stack, there's a meaningful decrease from the planar faces to the ones on the corner of the bricks, and that will, of course, also lead to differences in power output. What can we do in the future? Which may or may not be me. In first of all, GPU acceleration. This is something that I have wanted to do for a long time, including putting it onto multiple GPUs. This problem, like I mentioned at the beginning, is massively parallelizable, and this is a great way to accelerate the runtime of the solver, particularly for large problems. There are a couple of things that need to be handled before that can happen. Number one, handling memory better. Memory is currently not allocated as efficiently as possible, and it would exceed the RAM of the GPU cards pretty quickly. The second is using SAI-aligned algorithms. And what I mean by this is because the singularity integration algorithm extracts the boundary of the second surface, we don't need to care about any of the triangles that are within that boundary. So if we can find a way to extract those boundary edges, we can integrate across just those rather than everything else, which will make the entire solver faster. That's wonderful. The problem is then our blocking algorithm will break because we're no longer considering rays between all of the triangles. And so we have to also add in a new way of doing that. And Eliana has done some work on that as well, which would be great to include in Open View Factor. Element pair refinement is a wonderful way to handle the inaccuracies due to poor element qualities at the boundaries of shapes, like we saw with the squares and the circles as well, where we can identify characteristics of poor elements, poor element pairs, and refine them accordingly in the solver itself to avoid getting poor numeric results. That's not currently implemented, and I would love for that to happen at some point. For RTG view factors, there are a ton more places in the RTG to evaluate, and those should all be done. And then as a pipe dream, injecting these things into commercial solvers like ANSYS, for example, finding a way to take the high fidelity view factor results from Open View Factor and porting that into radiation solvers. I know that it's been a pipe dream of some in our group for a while, and it'd be great to see if we can figure that out at some point. Last thing, anything else with view factors? This is a general purpose view factor solver. It's not built just for RTGs. So if you have a problem that uses radiation heat transfer, by all means, use Open View Factor, and it will go well. Thank you very much for joining me and for listening.
We'll now open the floor to questions from the general public.
Yeah, so I've got a question. Might be a little bit basic, but this was reference to slide 75. Why you said that the shoes 2 and 3 were getting less view factor. What's the I would have thought looking at your diagrams that there'd be some symmetry involved and they would all be getting roughly the same. So that's surprising.
So this is caused by the fact that it is on the corner of the bricks. So these two are facing the faces of the bricks, whereas these are on the corner, and so they're just not viewed as highly. It's not like they're being viewed, a quarter of the amount. It's, from 12 to 10-ish on 10^-4. So it's not like a gigantic difference that would be a cause for concern, but it is definitely different. Yeah.
What are the error estimates on your converted values?
Are you referring to these or?
Yeah, sure. What are the error bars?
So I don't have specific error bars for these values, but I did. I took the mesh refinement levels for all of these studies, and then I upped them by quite a bit. So the studies for all of these are using 3.5 billion element pairs, which is higher than that graph goes. So if we're taking this at face value, it's on the order of 10^-8, I'll say. My estimate.
Is that an analytic estimate from your quadrature rule?
No, they're like these are kind of parallel plates. Obviously they're shifted, but that's the best that I have done in terms of like estimating it. Yeah.
Is there currently some tool out there for this already, and you can compare the performance of what you created to that, or is this something you know?
Yeah, so first of all, commercial solvers like ANSYS have tools built in to compute view factors. They're using a different method altogether. Part of the purpose of this work was to use quote unquote first principles, meaning going back to the equation itself and discretizing it as closely to the original as possible to get as high fidelity view factors as possible. The other purpose of this was to be able to use a software to get view factor results by itself, where in ANSYS and other solvers, view factors are not treated as a result themselves. They're just baked into the radiation heat transfer component. And that's part of why it's difficult to inject this into commercial solvers. But that's probably the closest you can get. Other institutions will sometimes have in-house codes that they write themselves to be able to do things. And this is hopefully to serve JPL in whatever they would like to do in the future.
Anything for you, Dan?
He's not hangry today. He ate food before this.
That's why you're
Yeah.
Any other questions from the general public?
I have a question.
Oh, Shane has a question. Shane, go.
Yeah,
for it.
yeah. So I have a question about the BVH. So,
Yeah.
you know, as I understand it, the BVH is not supposed to yield a different result, but is supposed to speed up your checks for various shadowing elements. Now, when you do a BVH over a mesh, as I understand it, you kind of have a choice of how fine you want to make the mesh, or you know how fine you want to make the neighborhoods, and you're sort of trying to trade off between checking fewer MTI elements and also kind of creating this BVH. So did you get a chance to explore that kind of tunable parameter of BVH neighborhood size? And could you speak to that?
Yeah, I did. For everyone in the room who may not have heard that, Shane's question is in reference to the BVH. Let me just slide back to that. Sorry, there are a couple hundred slides. Here we go. So Shane's question is in reference to the BVH structure. Right now, this structure was generated where each box is housing approximately 2 triangles per box. And Shane is referencing the fact that you can change the number of triangles per region to, you know, in theory, maybe make the computations more efficient. I did, in fact, play around with that a little bit, and it did not make any meaningful difference. If anything, it actually made it less fast, just made it slower. But that actually speaks to part of why BVH is so complicated. Not only is the code itself just more involved than the MTI application, but the BVH also has these parameters that you can tune, like the number of triangles per box. And you can also change how it is generated by adjusting like which axis you split boxes along. And okay, we're gonna take another tour through the slides for a minute so I can get to this. But you can adjust which axis things are split around. Oh, we're getting close, hold on. Okay, so for the BVH generation process, we're taking the box around the entire thing and splitting it roughly in half. This is using a cost algorithm. And right now, the axis I choose is somewhat arbitrary. I'm picking one axis instead of doing all 3 of them. And you know, we're going around all of these things. But if you wanted to tune like which axis you're picking to split around, or how many sections along the axis you're picking to do that, then you could, and that would change how the structure gets generated and therefore how you traverse through the overall thing. And that could affect runtime. In my experience, I think the implementation is just taking up too much of the poor performance, and that's not making any meaningful differences right now.
Yeah, that answers my question. Thank you.
Cool.
Last chance for questions from the public.
Yeah.
Can you see your quadratures again from like the very beginning? Sorry.
one more tour of the slides.
They're nice to look at.
There is a way to type the number of the slide you want.
Yeah, I'm in Adobe Acrobat Reader and I don't know how Adobe software works. So we're just gonna, where are we going?
Keep going back. Oh, governing equations, yeah.
This?
Okay, so when you do this, your integration points are what?
I'm doing just the centroids of all of the triangles. There is Gaussian quadrature. I did not implement that into this work. I have experimented with that in the past, and it did kind of help with things. But here I'm just relying on mesh refinement to kind of get the same thing. Gaussian quadrature, I can add that to future research.
Okay.
Put that on
That was
the
gonna be
list.
my question.
Yeah, put that on the list.
Because like, you might get a better speed up with respect to the number of elements, or better speed up on convergence with respect to the number of elements if you do Gaussian quadrature or something like that instead of just straight mesh refinement.
No, it does converge a little bit more quickly, but it's also a little bit more sensitive to poor elements, which is part of why I didn't include it here, particularly for the rectangles. All of those cases, because of disk mesh, will have some of those skew elements on the boundaries, and the quadrature implementation there would cause problems, to say the least.
So you're essentially just running the midpoint rule.
Yeah.
Yeah, okay.
Yeah.
Non-engineer, I want to ask you, what is the significance of this work in the world? What is the value of it for people like me who have no knowledge of any of what you've been talking about today?
Unless you feel like learning how to build C++ code, for you specifically, maybe not that much.
I mean, the application of it.
Oh, the application.
What is the
Yeah,
value
yeah,
of
yeah.
the work in the world in general?
So there are a couple of different routes I can go with that. Given that I'm applying this to RTGs in particular, the hope is that NASA can make better RTGs for more powerful and longer lasting missions in the future. And space missions are always good for humanity, unless they blow up on Earth again. But in general, space missions are great for humanity. We've found a lot of research from NASA from doing missions about that. And in general, increasing our understanding of space and planetary bodies outside of Earth is a good thing. It helps us understand how the universe works and how our world works. And that is always going to benefit us in some way, even though we can't predict what those ways are. The other answer is that view factors and radiation heat transfer in general are used all over the place. And having an open source utility to calculate view factors can help more people do better analyses of radiation heat transfer and make things like buildings more efficient, for example, of absorbing and re-radiating energy throughout the day.
Bobby, do you have anything?
No.
Okay.
Let's give Bob a round of applause.